Alright guys, so this is our last of the 3 videos for properties of logarithms, and this is going to be change of base. This is something that's really almost obsolete right now with new calculators because you can evaluate basically a log of any base with that calculator, and we'll talk about that too. But in general, change of base is a property that we can use to rewrite any logarithm as the division of 2 logarithms of any base, right? So right here, one of the things that made this useful was, it used to be that our calculators could only evaluate common logs, log base 10, or natural logs, log base e. So right here, if we had something like log base 4 of 64, we could represent that as the division of 2 common logs, the common log of the input, 64, divided by the common log of the base, 4, and type that into our calculator and solve it. Or we could represent this as the natural log of 64 divided by the natural log of 4, right? And both of these guys would give us the same number. Now, log base 4 of 64 is something we can evaluate on our own. Right here, what we're asking is, what this log is asking is, what do I have to raise 4 to in order to get 64, right? And I can raise 4 to the 3rd power and get 64. So right here, we could say, right off the bat, that log base 4 of 64 is in fact 3. But if we did this, if we used either of these 2 expressions, we type them into our calculator, we would see that the common log of 64 divided by the common log of 4 will also give us 3, and the natural log of 64 divided by the natural log of 4 would also give us 3. So right here, just a little bit of sort of processing for us. Now, we'll go back and forth and talk about some of these as we go through. What I want to do right now is sort of prove to you guys this property right here. So let's say we've got log base b of x. Now we know log base b of x has to equal some exponent, right? So let's say it equals the exponent k, right? Now at this point right here, I could rewrite this guy as b to the k power equals x, right? Then, right here, I could, let's say, apply the natural log to both sides, and that would give me the natural log of b to the k equals, right here, the natural log of x. And now at this point right here, with properties of logarithms, I can say that this exponent k inside my natural log, I can throw out front and make a multiplication of k. So I can call this guy k times the natural log of b equals the natural log of x. And then we're one step away right here because all we have to do is divide on both sides by the natural log of the base b. And we will get our change of base, which is basically log base b of x equals k, and k equals right here, the natural log of x divided by the natural log of b. And that is the proof of change of base. So right here, we can go ahead and evaluate all these with change of base. We can go ahead and do that in our calculator. Why don't you guys go ahead and do that. We'll pause the video and then we'll bounce right back and look at all these guys in the calculator. All right, so what we've done is we've rewritten all these guys as the division of 2 logs of the same base that we can evaluate in the calculator. So right here, we'll take out our calculators and start looking at these guys. And we'll evaluate these change of bases, but then we'll also go back and talk about how we can evaluate a log of any base in the calculator as well. So right here, the first one we're looking at is log base 0.5 of 12, and that's going to equal the common log of 12 divided by the common log of 0.5. So right here, taking out our calculator, we can type that in, common log of 12 divided by common log of 0.5. And right here, when we evaluate that guy, we get negative 3.584962501. If I wanted to evaluate my log base 0.5 of 12 directly, I could go to math, right? On the newer calculators we have this, and then right here at the bottom of that list under math, right here I can see I've got A as log base. So right here if I press enter there, I can type in any base I want, 0.5, right? And then I can evaluate log base 0.5 of 12, right? And that's going to give me right here my negative 3.584962501. So right here we can basically do that with all these guys. Why don't you go through and evaluate all these logarithms with either change of base or the log base of your choosing, or log base, not of your choosing, of the log we've actually got there. And we'll come back and look at those answers in a second. Okay, so first off, interestingly enough, what we're seeing is not only does log base 0.5 of 12 equal our negative, approximately negative 3.58, so does our log base 2 of 112. And so what we can do here is we can look at our two different expressions and see that they're actually pretty similar. So right here, if we look at the common log of 12 over the common log of 0.5, first off what we can say is the common log of 0.5, we could also write as 1 over 2, right? And now right here, let's represent our log base 2 of 1/12 as the common log of 1/12 over the common log of 2. Now right here, what we can say is that our common log of 12 over common log of 1/2, we could represent as the common log of 12 divided by the common log of 2 to the negative 1. Similarly, right here, we can represent our common log of 1/12 over a common log of 2 as the common log of 12 to the negative 1 over the common log of 2. And now right here with properties of exponentials, basically what we're seeing is we've got that exponent of negative 1 inside these two logs, and we can throw it out front and make it a negative, right? In the denominator for our first logarithm and in the numerator for our second logarithm. But basically, dividing by a negative is going to give us right here the same thing as just throwing that negative out in front, which is going to be right here. Let me see how I can write this. What both of these logarithms equal, which is negative, and then common log of 12 divided by the common log of 2. So an interesting piece in there, we can see how these two logarithms are equal, and they both equal negative common log, or natural log if we wanted to say, of 12 divided by common log or natural log of 2. All right, so the rest of these guys we can basically just type into the calculator. This one we can also evaluate right here. Log base 3 of square root of 27. We could say 27 is 3 to the third power, and that square root is a 1/2 power, so we could call this log base 3 of 3 to the 3/2 and evaluate it that way as well, right? What do I have to raise 3 to in order to get 3/2? That would be 3/2, but in our calculator we should have seen the exact same thing. And right here, finally, in this last one, we can just type this guy into the calculator. 12, log base 12 of 259, and you can type that in either with change of base or with the log of the specific base 12, and you should get 2.2362. Okay, so a practical use of change of base, or I mean, you know, again, all of these things we can do in the newer calculators anyway. But right here, one thing we can do with change of base is recognize basically the property of all logarithms, where basically a log of any base, right, we can really represent as basically equal to any log multiplied by some constant. What am I talking about? Right here we've got the function log base 1/2 of x. Right here, if I represented this as, let's say, the natural log of x divided by the natural log of 1/2, then right here I could see that this function is equivalent to 1 over the natural log of 1/2, which is a number, times the natural log of x. And right here we could type the natural log, 1 over the natural log of 1/2 in the calculator and get that constant. So 1 divided by the natural log of 0.5, or 1/2, gives us approximately negative 1.44269. So right here we can call this roughly equivalent to, or basically the same graph, very, very close to the same graph as, negative 1.44, I'm going to call that 27. Oh, I'm running out of room here to move this guy over. Oops. This guy over a little bit. And then that's of the natural log of x. So basically right here, these two guys are going to be roughly the same graph, right? We have to round this guy a little bit, so he's not going to be exactly log base 1/2 of x. But if we type this guy into the calculator either with this form, with this form, or with this form, we would get the same graph. And right here, one of the things we can recognize is that that graph would be vertically flipped natural log. So right here, basically what we would get is something that's going to look a little bit like this. And right here we can do some analyzing of this graph. Right here we can say the domain is going to be the same thing as basically any log base whatever of x, which is basically from 0 to positive infinity, right? We can't have x be negative or 0, right? We could say the range of this guy is going to be the same as if he were right side up. So right here we would say negative infinity to positive infinity. He is not increasing anywhere now. Now he's decreasing on the domain. And he is unbounded. He has no extrema. He does have an asymptote, x equals 0, and his end behavior, as x goes out in the positive direction, is now going to be negative infinity. Okay, so this last video turned out to be a little longer than I thought it would. Some interesting points to hit, though. And right here, I'll see you guys on Monday with a worksheet. I think everything else we'll touch on Monday. All right, see you guys then.